Hello everybody and welcome to today's webinar. My name is Jordan McGrath and I'm one of the regional managers with C-Therm Technologies. Very pleased to join me today is Sarah Ackerman, our lead application specialist, and Michael Landry, our thermal scientists from Thermal Analysis Labs. Today's webinar will run about 45 minutes to 1 hour. All the telephone lines have been muted to preserve the audio quality. A recording of the webinar will be posted on our website afterwards for review. There will be an opportunity at the end of the webinar for Q&A where we will unmute the lines and questions may be asked. There's also a chat box on conference that you can ask questions at any time and we will answer at the end of this webinar. Before we get into today's application slides presented from Sarah and Michael, I want to share a little bit about C-Therm Technologies. Our goal and our mission at C-Therm Technologies is to simplify thermal conductivity. We do that in a lot of different applications and we support many different users with different materials and different focuses of their research. Everything from batteries to textiles, we work in the nuclear field, explosives, building materials, polymers and insulations, and many more. C-Therm are niche specialists in thermal sensor technology solutions. We're a Canadian company based in a province called New Brunswick, and we focus on simple and fast measurements of thermal conductivity and thermal effusivity. We help different organizations and researchers accelerate their thermal testing in-house in different sectors, including research and development, production, and quality control. We have a few different awards that we like to show off here. The first is a pretty important one in Canada called the Manning Innovation Award, where the original inventor of the technology was awarded $100,000. More on a global stage, we've been presented the R&D 100 Award, where different inventions such as the BlackBerry, anti-lock brakes, Polaroid film, and the ATM also lie in that category. We're a global company at C-Therm with over 50 global partners around the world who support our users before and after the sale of our technology. We're located right here in New Brunswick, Canada, but we truly have a global reach supporting many different organizations and applications, some which are listed here to the left. To date, we have over 700 thermal analysis clients worldwide that we all support. Providing an overview now of our technology and our solutions that we offer, there's a couple different options. The first you'll see here to my left is the TC kit, which is really designed for researchers in the academic sector who might have budget constraints or limited resources but want an in-house capability solution to measure thermal conductivity. This solution is under $10,000 US and is a lower cost solution to help give you the data you need now. Looking at the more versatile and robust platform that we offer would be Trident. It's one instrument that offers 3 different transient techniques. If you're a researcher interested in textiles and fabrics and more focused on quantifying the touch properties of your materials, we would guide you towards the TX Touch Experience platform, which quantifies the sensation of touch through thermal effusivity. Today's webinar, though, will be focused on our Trident technology, in particular this sensor right here, the Modified Transient Plane Source. But I want to share a little bit about each of these capabilities found on the Trident platform. C-Therm believes it's better to have options So we've designed a platform for researchers that can be configured to what fits your needs and your budget using these three different sensors you see here. These sensors are the three most prominent transient contact-based technologies found on the market, and we're designing and offering them on one platform. Starting with our Flex technology, Flex offers the most control over your power and your timing parameters. It's really meant for more experienced operators and users who want to have the ability to control the power and the timing of their experiments and when they're collecting data. The transient line source, what we call needle, is a very robust and strong sensor. It's meant for higher viscous liquids, polymer melts, slurries, granular solids. Some technologies might run into an issue of bonding and adhering to the sensor. Transient line source allows you to collect data with those types of samples that run the risk of adhering or bonding to other types of sensors. The heart of Trident and C-Therm is the Modified Transient Plane Source, which think ease of use, precision, accuracy, robustness. It provides the ability to measure liquids, solids, powders, pastes, gels. A very broad range of materials can be used on this technology and has been adopted by many different industries. Before I lead into Sarah and Michael's application notes, I want to share a little bit on the Modified Transient Plane Source. The MTPS is a one-sided sensor, meaning you only need one sample to characterize your materials. The heart of the technology lies here in this green chip. It's about 17.8 millimeters in diameter and is the active part of the sensor where your thermal conductivity data will be extracted from. Looking at the principles of operations and how it works, it's a very quick and easy test. So a known current is applied which electrically heats the green sensor chip. That results in a heat pulse into the sample, and the voltage drop over time is monitored. And what your raw data looks like is something like this. Your guard ring on the outside is another very important aspect of the sensor chip, which allows for a one-dimensional heat transfer into the sample. So your sample, and the benefit that offers is your sample only needs to cover 17.8 millimeters in diameter for solids, and you need a very small volume when you're measuring liquids or powders. Back to what the raw data looks like, you have your voltage time curve, which is calibrated to your delta T over time. And these slopes are inversely proportional to thermal conductivity. So for something like a foam that's very insulative and low in conductivity, you're going to have a much steeper slope than something conductive like a copper or a metal sample. Trident is offered on one platform with one software interface. It can be configured to any three options that I discussed earlier that best fit your samples and what you're really trying to achieve in your lab. I wanted to share a testimonial from Tuv Sud based in Switzerland, who was one of the first adopters of the Trident platform. Delphine mentions that using the Trident system for thermal conductivity testing of our process safety studies and related contract testing has provided our lab with invaluable new capabilities with great support from the team at C-Therm. With that, I'll transfer it over to Michael Landry, who's going to discuss one of my favorite application papers out of Auburn University related to additive manufacturing. Michael and Sarah?
So I'm going to discuss an interesting paper that was from Auburn University, specifically headed by researcher Nima Shemasai, who looked at, investigated the effect of recycling powders on additive manufacturing parts, and specifically the tensile strength and the fatigue of these parts. During a typical additive manufacturing process, you have your manufacturing bed right here, which is constantly being fed by a roller through which powder delivery piston will push up powder, and the roller will roll onto the powder manufacturing bed. Using a scanning head on top, we're able to selectively found and selectively melt the additive manufacturing powder to create your part. And as the roller comes across, you build up your part one layer at a time. So the objective of the research was to look at the effect of recycling these powders. And this is a very important green and a very important economical aspect, as we're looking at these powders, which are based on titanium, around $300 to $600 per kilogram. So being able to investigate and find methodologies which are able to recycle these powders is very important for the industry. So specifically, they found in the research they wanted to minimize fatigue behavior. They wanted to make sure there's no diminishment on the quality of these parts. And they did this by investigating the thermal properties of these types of materials, these powder materials. So specifically, what they did is they investigated the thermal conductivity of fresh virgin powder versus used powder, which was used 15 times. What they found was the surface roughness of the materials and the surface roughness of the parts that were being manufactured was slightly more rough with powder which was used 15 times. And the way that they explain this is by looking at the thermal conductivity, which was measured using our MTPS sensor. They were able to calculate the thermal conductivity of new versus used powders, and found that there is an increasing tendency for the thermal conductivity to go up with more used powders. And this was important because thermal conductivity was, if it's lower than used powders, will lead to higher heat accumulation in the proximity of the part, which will increase the surface roughness of the part which is being manufactured.
All right, so I'm going to speak a little bit to some powder blend uniformity testing that we did, that we had published with a group out of Cinnaminson, New Jersey. Hagenus Corporation is the group's name. So we published this, I published this together with those researchers from Hagenus Corporation in the International Journal of Powder Metallurgy, and it was an award-winning paper, so we're pretty pleased with the work. And so really the significance of this to additive manufacturing processes is that in order to optimize your AM process, a lot of people are trying to take more of a rational approach to AM process modeling and process optimization. Right now, a lot of the AM devices out there kind of act a little bit like black boxes, where you tweak different parameters on the outside and you're not really sure how or why it's affecting the quality of the product that comes out at the other end. So a lot of groups out there are looking to better characterize what is actually physically occurring during the process. And to do this, you need to have a good idea about what you're starting with, in addition to what's coming out and what's going on during the process. So this is more looking at what is this that you're starting with, how uniform is what you're starting with, because blend uniformity for a lot of these metal alloy blends is key in terms of determining the final quality of the part. So getting into a little bit of powder blending, it's a really common way to make powder mixes for metallurgy, both for metal injection molding, but also for additive manufacturing processes. And usually what you're going to do is have a blender that can blend, depending on the needs, between about half a ton up to several tons, or in some cases tens or hundreds of tons of the material. And the most common blender is this sort of blender here, which is kind of a double cone blender. You can see it's quite symmetrical in terms of its construction. So there's a couple powder blending issues that are pretty common and have quality control implications in terms of the final product. So one of the most common ones is segregation. So if you have a well-mixed powder here and then you overblend it, sometimes you can get segregation or what's sometimes called deblending of the powder. And the segregation can be caused by a variety of factors, including particle size, density, and material chemistry. But even for unstable blends that will eventually segregate, you can usually find a shorter blend time or sometimes a longer blend time that will let you avoid the segregation. And in some cases, the segregation is irreversible. Like once the blend segregates, it's not going to go back into a good blend. And in other cases, it's not irreversible, and if you process it a little more or under certain different conditions, you might be able to get it to become a well-behaved blend again. Another common cause of powder blending problems is caking. So this can occur when static powder self-adhesion or when moisture kind of cause a cake of material to stick to one part of the blender and not go into the full blend. So in this case, you can see an image, a dark cake of the unblended lubricant, which was actually stuck to the top of this blender, and it fell off the top onto the powder blend when the lid was open to take this photo. So that's an example of what caking looks like in practical terms. And there's a few issues in terms of process optimization for powder blending processes themselves. You need the correct blend time so that you don't waste energy blending a blend that doesn't need to be blended anymore. And also so you don't waste money and product by overblending and causing segregation that may or may not be reversible. Variability in the source material is often a major cause of process issues in these sorts of things. So if you have a source material that, for example, you're getting your iron from recycled iron, you're going to have a lot of variability in terms of the quality of the iron coming into your process, and that's going to lead to variability in terms of what's coming out of your process. So what you can do is design, if you understand the blend well enough, you can design a process that will compensate for starting material variability so that even if your starting material is variable, you get a consistent end product coming out the other side. And that's where we get into using thermal effusivity as a process monitoring tool. So this system here is called the Effusivity Sensor Package System, and it's a process analytical technology system using the same technology as the Modified Transient Plane Source sensor my colleague Jordan was speaking to earlier. So you can use this package to monitor blend uniformity online, at line, or even inline with the process, depending on the needs of the group with the process. So there's generally speaking, 3 different types of blend. Type number 1, unknown blends, are blends where you don't really fully understand what's going on. And in a lot of powder blending processes, this is the most common type of blend. Just because usually groups dealing in powder blending, when they find a set of parameters that work, they don't want to tweak with it. Why fix what isn't broken? The second case is basically a best case scenario. The sample is stable. It doesn't matter how long you blend it. If you overblend it, that's fine. You're just going to waste a little bit of energy, but you're not going to waste the product. So that's a really good case scenario, because a stable blend is not going to be at risk of segregation, and it's not going to be very sensitive to slight variations in the process conditions. The worst case scenario, and quite a bit more common than the stable blend, is the sensitive blend. And this is a process where the blend itself is sensitive to blending conditions and to changes in the amount of blending time. The product may segregate, or you may get caking if you go too long. In some cases, you might have an additive that as the powder blend continues and it heats up, you might have an additive that undergoes a phase change if the blend heats up too much, and then that could cause some sort of irreversible change to the overall quality of the blend. So lots of different things can cause a blend to be sensitive, but if it is sensitive, you need to know, and you need to know how to adjust to deal with its sensitivity. So how does this work in a real-world situation? This is a very quick example. We covered a bunch of other permutations of things that could cause it, including looking at spotting additives as they're added into a blend, those sorts of things. But this is just one plot from the paper that we wrote. And you can see here we've got 4 different components in here, and we can identify, using the thermal effusivity, a region where the blend is stable, and then a region where the relative standard deviation starts kind of getting spiky, and it spikes up in some cases above 10% relative standard deviation. Whereas in the stable blend region, it's typically less than about 3.5% in most cases. And this kind of increase in the relative standard deviation between the sensors indicates that there's a greater difference in regional variability between the 4 sensors that were in, or the 3 sensors rather, that were in the lid of the blender. And that indicates that we're getting some sort of segregation or deblending phenomenon occurring. So we're getting some demixing. Looks like it demixes a bit, and then it goes back in. Then it demixes a bit and goes back in, demixes a lot, goes back in. So this is actually a case where it's a unstable blend, but you can recover if you overblend. So this is a better case scenario than one that is simply unstable and won't go back after it's destabilized and segregated. Going over to the next one. This one is an application note called Design of Novel Materials for Additive Manufacturing, Isotropic Microstructure and High Defect Tolerance. This is a paper published in Scientific Reports done by some clients of a partner group to C-Therm called C-Therm Instrumentation. So C-Therm is a group that focuses in on high-end thermal analysis and calorimetry equipment. They're focused mainly in on extreme environments or very high sensitivity operations. They're really the best in the world at what they do as far as high temperature and very challenging applications are concerned. So we actually use them in our testing lab for our contract testing services for thermal analysis labs. We have a few of their instruments, and my colleague Mike Landry here will be highlighting some heat capacity measurement we did with one of their instruments later in the talk. So this is looking at a process called electron beam melting, or electron beam manufacturing in some cases. And what it does is it shines a very high power beam of electrons at powdered metal to melt the metal and apply subsequent layers to a part or a workpiece in an additive manner. So it is a method of 3D printing. But instead of using a laser like some methods do, it just uses a beam of electrons. In the next slide here, you can see that the authors in the paper speak to some of the flaws and the faults that can be introduced by the electron beam manufacturing process. They're prone to some quality issues caused by different types of cracking. Faults can include defects or cracking, as you can see in some of these cases. They can also include surface roughness, which you can see a little bit of here, as well as anisotropy of the thermal and the mechanical properties. So you think about how this process occurs. You're laying down layers of the metal with the electron beam melting, and because it's being applied in layers, it's very easy to have the microstructure end up oriented, or also because of the nature of the melt and the serial melt and refreeze that these alloys experience, it's also possible to get strain accumulation inside the structure of the part. So that can also cause some anisotropy in the mechanical properties in addition to the thermal properties. So the goal of this paper was to design new materials for this melting process that would exhibit improved cycling performance and improve crack resistance. And what they wanted to do was construct a phase diagram so that they could take advantage of transformation-induced plasticity in the alloy, and also some twinning-induced plasticity to reduce the likelihood that the part would crack. The technique that was used was called differential thermal analysis, or DTA. It's a very powerful technique for identifying phase transitions in materials. So the technique that was used in particular was a high thermal sensitivity tri-couple DTA process. So tri-couple DTA uses 3 thermal couples instead of the classical 1 thermal couple, and because they're arranged in a pile, the sensitivity is additive. So you get about 3 times the sensitivity of a classical DTA technique, without losing the advantages of DTA, which include the low thermal mass of the sensor, which makes it very responsive to the onset temperature of certain signals. So this is looking at the DTA of one of the specimens that was examined in the paper. And you can see that there's a lattice phase transition visible here between about 1200 and 15 degrees Celsius to 1225. We can also very easily visualize the melting point with this large endotherm. So what this is able to do is provide evidence for where the FCC to combination BCC and FCC transition which is predicted on the theoretical phase diagram here. So moving into the next slide, this is microstructure and properties of laser engineered net shaping manufactured nickel titanium shape memory alloy. So laser engineered net shaping is an additive manufacturing technology. You can see a photo here because the Sandia National Labs actually developed this technology, and this is a photo taken from their website to show you what it looks like in a real world scenario. So instead of the way that most additive manufacturing technologies deal with adding the different layers, most of them use a bed of powder. This technology, the powder is being supplied by these tubes here. So they apply the powder down basically where it's needed, and that gives them a more tight control over where the powder is added. The other benefit of it is that you don't need a huge bed of powder, so you don't wind up wasting as much of the powder material, which is quite attractive if you have an expensive starting material, for example. So the basis of the work that they were doing here is looking at nitinol, or the nickel titanium shape memory alloy. And it's used in several industries, basically to act as a physical switch. In this case, you can see a photo of nitinol both before and after it's been placed in some hot water. What they did was basically take a paper clip and then bend it out of shape into this kind of tangle here, and then stick it into hot water, and it regained its original shape. So this phenomenon is called super elasticity, and this shape memory alloy exhibits this property near the martensite transformation temperature. And you can actually tune the martensite transformation temperature by changing the composition of the alloy, which makes it very useful to make mechanically actuated thermal switches and similar sorts of things. So there's a few challenges when you're working with nitinol. One of the first ones is that it tends to stress heat, and the actuation frequency, because it stress heats, is dependent on thermal management. If you don't pull that stress heat away efficiently enough, it's not going to be able to actuate as often. It's also traditionally been considered pretty difficult to weld and also machine. So you need to understand the thermal properties very well, which you can do by DSC. And you also need a firm understanding of the phase change behavior, which can be done by a combination of techniques, such as XRD, DSC or DTA, and dilatometry. DTA is usually the best if you're looking for the onset temperature. DSC, you can pull the data out as well. It's just not going to be quite as sensitive to the onset temperature. And dilatometry lets you look at coefficient of thermal expansion, and some phase changes are visualizable on dilatometry if the phase change is associated with a change in the CTE of the material. And then finally, you need to understand what the fatigue behavior and the life cycle is going to look like for the material. So most often, people are going to be using a technique called DMA, or dynamic mechanical analysis, to achieve that one. So this webinar, we're going to be highlighting the DSC work that was done on it. For this work, they used a C-Therm Sensus TG-DSC, which employs a very unique technique called the Tian-Calvé technique. And we call it 3D DSC because the heat flow sensor, instead of being flat and plane shaped the way most heat flow sensors are in DSCs, instead, it's a ring thermopile, and a series of these are stacked up, so you wind up with a cylindrical heat flow sensor. And the cylindrical heat flow sensor has a number of different advantages to it. The biggest one is that because it can pick up or detect rather both convection and radiation in addition to thermal conduction, whereas a traditional flat pan-style DSC is only able to detect thermal conduction down into the sensor. This kind of heat flow sensor winds up being much more sensitive to small heat effects, as the overall heat flow sensor efficiency is in excess of 90%, whereas a traditional DSC, the heat flux DSC sensor efficiency is going to be on the order of 35 to 40% at best. Looking at the DSC results here, you can look at the substrate and also the fully annealed powder. You can see the melting temperature on the heating and the recrystallization temperature on the cooling, in addition to being able to visualize the hysteresis in the two plots. And if you look at the annealed powder, you can see how the thermal properties differ from the substrate material. You can also identify a few of the phase transition onsets and peak temperatures with this data collection. Using DSC, you can also achieve examination of different velocities of manufacturing and take a look at how that affects the thermal properties. So this is looking at manufacturing velocities ranging from 1 millimeter per second all the way up to 30 millimeters per second. And velocities greater than 10 millimeters per second all are behaving quite similarly. So below that, the properties are quite sensitive, and above that, it doesn't seem to have much of an effect on the overall behavior of the alloy. Moving on to the next one, I'll turn this over to Mike, who did this work.
So I'm going to highlight some of looking at an additive manufacturing powder, and specifically what we can provide here at Thermal Analysis Labs. We recently acquired a DSC LabSys Evo, which has access to multiple different experimentations, including TG, DSC, DTA, and a CP rod, able to achieve and measure thermal effects from 0 to up to 1600 degrees Celsius. Now, what's really important when you're looking at the thermal effects of titanium or any types of additive manufacturing powders is being consistent between batches. The effects and the strain and the physical properties of each of these manufactured parts can dramatically change based on the physical properties of the powder that you're using. So it's important for manufacturers to make sure that these are consistent between batches. And one way we can do this is, as we've shown today, through thermal conductivity, but also through the characterization using CP, or heat capacity. So it's typically very easy for us to do this. You run a typical DSC, or differential scanning calorimetry experiment. In this case, we'll have a couple different curves. We have one that's with respect to the actual sample, so AS. One that's with respect to a known standard. So typically the known standard would be a sapphire rod provided by NIST, and these have very characteristic heat capacities with respect to temperature. So it's very well known, and by comparing the effect of the sample that you're running with respect to the known with the known heat capacity with respect to your typical heat capacity generated from DSC runs, we're able to back calculate the actual heat capacity of your final product, of your titanium-based additive manufacturing powder. So this is exactly what I did in this run. We looked at stainless steel AM powder, and specifically from 0 to around 500 degrees Celsius. You can see that the thermal conductivity does change with respect to temperature, which is important to know as you're over time. But so by measuring this, we're able to show that specifically at different temperatures, the heat capacity of that powder with respect to the process that you're trying to generate. So if this is in a stream, you want to know specifically the stream is running at 200 degrees Celsius, we're able to calculate that heat capacity, which is very important when you're doing modeling of these processes in general.
Okay, so that's it as far as the prepared content. I would just like to urge people online, we're going to start our Q&A session very shortly, but ahead of that, if you would like some more information about any of the things that we've talked about today, or if you have any issues that you may think, or that you think our capabilities may be able to help with, please feel free to mention it during the Q&A session or in the chat box below. Well, if you have any questions that you don't really feel comfortable asking in a public Q&A session, please feel free to ask in the chat box. We will keep any questions asked in the chat box completely anonymous. As well, if you want any more information on the thermal conductivity platform described earlier and used for a lot of the work presented here, you can go to tridentThermalConductivity.com for some more information there. Thank you for attending the webinar. We'll stop the recording just now, and then we'll get started with the Q&A session.